Sorry, they're managed.
Is the mic working? Hope everybody admired the preparations of the national holiday. I was going to say something else, but I'll be politically correct. I'm Karen Makou, for those who don't know me. Very happy to share this session, which is the first set of papers that a subset of the papers that are in the special issue that we talked about yesterday in the Journal of Development Economics. We have, unfortunately, one presentation less this morning. Because of a visa concern, so the positive spillover is that everybody that is here gets a little bit more time. So we'll have 25 minutes for each paper, with 5 minutes at the end. So hold off your questions and unless there's something super burning. And so we'll get started with Klaus Deininger from the World Bank. Floor is yours.
Microphone here, no? So I think, yes, I guess that is. So this presentation is about Ukraine. Let me sit here and that will be easier. Okay. It is entitled Using Free Remote License Data to Assess War-Induced Damage on Agricultural Cultivation. And it's, of course, with a couple of co-authors from both the National University in Ukraine and University of Maryland. The motivation is that conflict impedes agricultural cultivation, both in the short term, because it destroys crop and infrastructure, and of course in the longer term, because it, through mines and other unexploded ordnance, as well as lack of accessibility, measuring that is critical, because both for global supply estimates, especially in the case of Ukraine, which is a major producer of oil seeds and also grains, but of course also to see where do you want to target if you want to support farmers to actually deal with the fallout of that, or with mine clearance to eliminate the longer term negative impacts. But the accounts of how areas are affected, of course, differ widely, and since these areas are difficult to access, it is very difficult to get true estimates of that. However, interestingly enough, the few studies that look at these issues mainly use media-based indicators rather than spatially explicit indicators, and that's where we thought, and of course that is very counterintuitive, because agricultural damage should be observable through remotely sensed imagery. I think these media-based indicators may be very much biased towards more populated areas or media coverage in general, closer to infrastructure, that is not necessarily correlated to agricultural damage. So what this paper does is to construct an indicator of damaged land every 2 weeks using freely available satellite imagery. Now I lost my thing here. That is also very stupid. And using hand-labeled Sentinel-2 imagery, we check the robustness with various indicators. We link that to a machine learning model that uses infrared thermal indicators and burn scars. We'll probably not have time to go into that into too much detail. And we compare to commonly used media-based indicators, ACLED and UCDP, as well as government statistics. Of course, then this is the damage estimate part. Then, of course, since we want to see how this damage actually affects at least area cultivated, we use a panel data set of close to 10,000 villages over 2019 to 24, so both before and after the conflict. That was constructed using both Sentinel-1 and Sentinel-2 cropped areas. I think that has been and is being used by the government as well, even though it was also elaborated by our team. We look at regressions, both contemporaneous and true lags. So we also use spatial lags, and we see that the conflict has a persistent and increasing effect over time. And then I think we just replace the conflict indicators with 0, to see how the conflict effect varies if we use different measures to assess the conflict. And what we find is, and I'll show you the figures there, that the total damage is about 3 to 4 times larger if you use image-based rather than media-based indicators, and that also the geographical distribution is quite different. Especially, I think the one thing that is of course interesting is to see how it differs between areas controlled by Ukraine and by Russia, and we see significant differences there. So I think, as I already mentioned, Ukraine agriculture is still a key sector in the economy. It is about 10% of GDP and most importantly, 42% of the total exports. Oilseeds is a global supplier and maize for specific countries, especially in the Middle East, where there was a lot of scare about food security. It has very large farms, 1,400 hectares on average, with field size of about 70 hectares, which of course makes it much easier to detect issues and conflict. I think the estimates are that the conflict resulted in the displacement of about 8 million people, about 20% of the pre-war population. There are a lot of papers that use trade models to assess the impact of the conflict, but nothing on the micro side. What we do is we use 4 types of damage, and we do that with hand labeling. Of course, there are plenty of unemployed students in Ukraine right now who are happy to be employed in that, and where you can actually improve the economy. So I think we use cloud-free Sentinel-2 imagery, and we, as I said, we also combine it with a burned area estimate. And of course, I have to say that this is part of a much larger EU-funded project to prepare Ukraine for EU accession. I think we have been working on land markets, liberalization, assessing market power, and ways of regulating it. And also, I think what is especially, and which is, I think, linked to the spatial data that we are using here, establishing a farmer registry and creating the preconditions for distributing EU support, which I think is quite a complicated issue. So just to give you an example, so these are the pre and post images on Sentinel-2 imagery. The top one is a burned area. The second one is that you see whatever tanks or whatever moving on the field. The second one is both trenches as well as artillery shelling, which I think is the most difficult to detect. But of course, I think, and of course, the important thing, which is why also machine learning is difficult, is that these damage indicators are very transient. So I think within a couple of weeks, you essentially see them completely disappearing. So I think this one here, the top is in June. It's completely undamaged. In end of June, beginning of July, you see something, and in August, it's gone. So I think it's a much harder problem than the one that Ariel presented yesterday. We also, to see whether this labeling is actually worth anything, what we did to select a couple of 5 blocks of where we had 3 independent annotators annotate the imagery. It was actually quite astonishing, the level of, I think, totally, if we include areas damaged and not damaged by fields not damaged and not damaged, we have 98.8% consistency. And if we look only at the damaged area, also, I think the share is quite large, where so in 1144 cases, all the 3 annotators agreed. So I think it is quite easy to detect these things on imagery. So if we look at this, how this evolves over time, this is 2022. So I think the red ones are the damaged areas by conflict. 23, you see clearly the front line there. I think there's a lot of damage here in 24, also in the Russian occupied areas, and that moves back a little bit to the damaged areas. So I think these are the data that we actually use. So I think on the so we have the 2, this is only for 2022, but of course we have the same thing for 3 and 4. So this is whether or not in the village crop was damaged. This is the hectares per village. VC is village council, and this is the total area for the all of Ukraine. These ones are planting and growing season for the summer crops. This is growing season for winter crops, planting season for winter crops, and and dormancy for winter crops. So these are what we use in the regressions. We aggregate the damages at the growing stage, and these ones are the indicators from battles from ACLED, just for comparison. This one is the illustration for fire detection. I think I probably don't have time to, so I think this one, I mean, it's essentially the same thing. And we use both, I think, firms data, which is a much higher frequency, much more lower spatial resolution. And then I think combine that with Sentinel-1 and 2 on the thermal signature, and especially also looking burn scars. Just to show you that ACLED data is not that precise. So I think the ACLED, so the village councils here are in white. These are the settlements. The green dots are where ACLED, and I think to know for ACLED, I mean, they put every conflict that is reported into the next settlement area, whereas the red ones are the fields that are actually damaged. So I think it's clear that both the intensity of conflict and also the location of conflict may be quite different depending on which of these measures we use. So I think if we compare that to ACLED, I think, and that is, I think that is thanks to Ariel who suggested that, we see clearly that where we have only ACLED, and of course you have a lot of urban settlements, urban areas where ACLED reports conflict. So we have a square population of almost 100 per square kilometers, where if we look at the combination, the union of image-based and ACLED, we see that that goes down significantly. And we still have a large number of images. But if we go, sorry, this one should be here. And if we look only at the satellite imagery, we are much farther from infrastructure and in areas that are much less densely populated. So clearly that adds some signal, I would think. And I think with the fatalities, it's even worse. I think so. We then aggregate the village, the amount of damage at the village level to put that into regressions. And I think the only thing that you should remember from this slide here is that that allows us to disaggregate into controlled by Russia and controlled by Ukraine. Although I think going into detail, I think since the front line shifted over time, we can discuss that if in the discussion if needed. What we see then is that these are just very simple descriptive statistics. We have 27.7 million hectares cultivated before the conflict, and about 25, so a net effect of -2 million hectares due to the conflict, just at the descriptive level. We can disaggregate that into winter and summer crops, but we see very clearly that that effect of conflict differs significantly by villages that were affected by conflict, where you actually even see some slight increase, which of course is due to displacement of farmers who were farming in conflict areas, who actually moved into the less affected areas, and a significant reduction in the villages where we actually see field damage occurring. So with that, we then estimate standard DID regression with 2 lags of the conflict indicator and also a spatial lag of the conflict indicator. And of course, we can then come with the village fixed effects and village times and region times indicators, fixed effects as well. And I think just to add, we of course include there also climatic variables, both the precipitation and the GDDs for the relevant periods in the growing season and their squares. So I think this is just, and this we get from NASA data that are now casted for the at the daily level or 6-hour level. So if we look at the regression, I think what we find is, and so I think the first one, this is damage in just a dummy. So I think I focus on the DA means damaged area, BA is burned area, and NF is the number of fatalities, which is here on the right. these ones here for ACLED data. So for the spatial data, what we see is that the coefficient increases significantly over time. So I think there is some persistence of conflict effects. Of course, all of them are significant. And that if we look spatial, if we look at the model with the spatial effects, spatial spillovers, we see that there are significant spatial spillovers. I think what we do, the way we construct the spatial spillovers is we give a weight, contiguity weighted, if the village is contiguous, it gets a weight of 1, and then it gets a weight of 1/2 if it's next to the neighbors. But I think this is quite robust. So what does that mean? If we aggregate over the 3 years that where we observe conflict, that is 22, 23, and 24, we see a total area of 85 million hectares. If we, okay, I'm almost done, so I think we should be fine. If we look at, this is from the spatial indicator, we see that total is 9.4 million hectares that is reduced due to the conflict effect, which is about 11%. If we look at the number of fatalities in ACLED, that would only be 3.5%. So I think it's a significant underestimation of the area of agricultural area that is affected by conflict. If we look at villages that are based on our indicators have experienced some damage, we see that this is clearly, so villages, essentially the spillover effect is 3.5%. These are the villages that have no field damage based on our indicators, whereas the villages that have damage, if I can find the thing, they have about, so there the cultivated area is reduced by almost 50%. And of course, that is not really detected if we look at the ACLED effects, ACLED indicator. So that is something where clearly our thing is interesting. If we look, this one is from government statistics. So I think if we look at government statistics that and I didn't go into that into much detail. I think we see that also there is a significant significant difference between almost the same as if we look at our village effect, our effects, even though I think the numbers are quite different between the villages that are affected and not. And of course, if we look at Ukraine-controlled and Russia-controlled, we see that the total area before the conflict was 7 or 13 million hectares in the 2 respective categories, that we see a reduction by 40% in Ukraine affected, in Ukraine controlled, and by about 30% in Russia controlled behind the front line. And that again is significantly different than what we see if we look at ACLED data. So I think with that, to conclude, that satellite data are better to assess damage from conflict than the media-based one, especially in less populated areas far from infrastructure. We see the negative spillovers and the accumulation of effects over time, and that the magnitude of estimates differ significantly between the 2 indicators, as I have illustrated. Thank you.
Right, so we have 8 minutes for questions.
Think in terms of, so we didn't try other units of analysis. And because there, of course, I mean, because that was already quite complex in terms of looking at the data requirements. So certainly, but I think that, and since we look at the field level, I think we are experimenting with and looking at more detail at the field level, because then I think you need to define first what part of the field is actually damaged and not, and how does that vary over time. So I think that is a problem that is a couple of magnitudes more complex than what we are looking at here. So I think that is something that remains to be done. In terms of other conflicts, I mean, I would think that damage is probably something that should be observable very, I think, quite easily, and that there, I think, also, especially as I mean, sensors are becoming more easy, better. So I think that is, in terms of the outcome variable, of course, the cultivated area, I think that is something that certainly will be more difficult, and that I think because there we have been quite lucky that we had the already existing data that we could use for that.
I found myself wildly underestimating, and this is a practical thing. Like, how much does this cost?
Of course, that is I think that's a good question, and I think it is something that we should look at. And because I've been pushing the team quite a bit. I mean, I think right now they actually have a machine learning model that uses that too. But I think the question was, and where they were, I mean, I think the detecting these very short signals precisely, I think, is something that is quite complicated. So I think I mean, they have been trying to do that through machine learning from the beginning, but I think the quality of the estimates was so bad that I think that is why the hand labeling was, and of course we are lucky in that sense that you had a lot of labor. That is easy which is something you may not have in other situations.
So, I thought we should,
Yes.
Still.
Yes.
Still need this ground. But rates of us thousands of hours to do these data sets.
And of course, I think one thing is that for the crop estimation, that also, I mean, there I think the ground truth and the ability of having the local team on the ground, I mean, was invaluable, because if you use some other data that are not locally ground truth, I think its model goes out of bounds very quickly.
Okay, Rapid came out of NASA Harvest, and I think their acronym reflects the fact that they are in emergency situations, and they're doing quick analysis of the impacts of conflict. So it'd be interesting to look into their work, but
of course, we are aware of the NASA Harvest people, and I think that I think fun. I think, and I mean, they're. I mean, the problem, and we have been discussing with them quite a bit, I think their problem is the lack of ground truth data. And that's why I think the estimates are more rosy than if you actually have the ground truth data, then I think things become a little bit more complex.
Do you think your results? Do you think your results are too much political, or how can you justify these numbers with the difficulties you had explaining to everyone around this conflict how to use them and interpret them? Because I think it's when you talk about the difficulties you had to go on the ground or to interpret these results, how this can be presented. Because we have difficulties with Ramsar to show it in a very natural, scientific way that we didn't succeed, actually.
Guidance on how to go about doing this based on the analysis you conducted?
I think, of course, what the government has been using the data for is to target support to specific areas where a lot of damage has occurred and where the front line has been shifted. So I think it was used extensively for targeting purposes. I think that is probably at the end. Of course, I think you see what also is, I think, relevant is that you see then you can use remote sensing and especially the estimates of dropped areas to see whether that support actually had an impact or not. I think we did some estimates of that, even though I think that also has some challenges. Of course, it's not completely, but that I think is and the second one is in terms of the demining efforts, which again is a form of targeting on how you actually can recover from the conflict. So certainly I think the recovery of the conflict is probably the most important thing. Unfortunately, the conflict is still going on. So we are not yet in that phase fully.
Yes, thank you for the interesting presentation. I was wondering whether it is possible to obtain these data for policymakers for use, or is it like confidential?
I think I think the crop data are fully public. I mean, that is on the ministry's website actually, and we got into big trouble from the World Bank because then somebody could discover. Or I think that because we are not allowed to put these things out from the World Bank, but it is on the ministry website. I think the estimates of the damage of the conflict intensity, I think they are available at the village level. But the remote sensing data is Sentinel.
Okay, we should move on. Thanks, Klaus. So we're going to move south. Jeff Bloem from IFPRI.
On here. Great. Oh, this is what I need. Okay, great. All right. So yeah, this is I think in the spirit of like many of the presentations yesterday, this is a paper that was originally just a regular RCT on agricultural technology adoption. I was presenting those results, and my co-author on this, Clark Blumberg, I should highlight his contribution to this, was in the audience and said, "Hey, like, have you thought of seeing the results of this intervention on deforestation?" And I was like, "Okay, let's talk about that." And then that led to this paper. Along the way, we sort of encountered some challenges that we had to overcome, and so I'll present results which I think are interesting, but I think the main takeaway that in addition to that, is that we came up with like a method of dealing with a problem that was sort of very acute in our context, but I don't think is unique to our context. So I'd be, I'm very curious about building on this work when using this method in other contexts, and adapting this method as necessary. So hopefully this inspires some additional conversations. All right, so just as a way to motivate, globally, shifting agriculture accounts for about a quarter of deforestation around the world. But there's meaningful regional differences in the drivers of deforestation. So in sub-Saharan Africa, our paper takes place in Nigeria. Shifting agriculture is the primary driver of deforestation. This is, some results sort of quantitatively differ. This is from Curtis et al. In Science from 2018. But the main point is that shifting agriculture is a main reason why we see deforestation in sub-Saharan Africa. And also sort of reflecting on the triple challenge, which I think as walking around, the FAO and seeing what their focus on, this idea is not going to be new to many of us, but it's to extend a sufficient and safe and nutritious food supply to 2 billion plus people who are experiencing food insecurity around the world, reduce poverty and improve livelihoods for 1 billion plus people who are employed along agricultural agri-food value chains, and then to do both those things by limiting environmental damage, forest and habitat loss, greenhouse gas emissions. Food systems are a large contributor to pollution. Agricultural expansion, as we just saw, threatens forest area. And so, figuring out how to achieve these first two goals while also limiting environmental damage is a significant challenge. Climate smart agricultural technologies represent, one possible pathway to address this. So, trying to increase agricultural productivity, reduce emissions, and also enhance resilience to climate shocks for farmers. The World Bank calls this the triple win of climate smart technology. However, even climate smart technologies have an ambiguous effect on deforestation, at least ex ante. So if the technology makes agricultural land more valuable, then farmers might be motivated to expand their farmland and increase deforestation if their farmland is adjacent to forested areas. There are many mechanisms in which this doesn't necessarily have to be the case, though. Imperfect factor markets, inelastic output demand, can lead to agricultural intensification of leading to less or no deforestation. So understanding this relationship is really critical to addressing this triple challenge of promoting food security, livelihoods, and limiting environmental damage, forest loss, and climate change. Okay, so in our paper, we used data from an RCT in Nigeria that promoted the adoption of urea supergranules. Urea supergranules is a technology that is a larger sort of pellets of urea that are deeply placed in the soil instead of, in contrast to being broadcast on the soil surface. When rice plots are flooded, the traditional broadcast method leads to a lot of nitrogen runoff, leading to a bunch of environmental damages. Urea runs into adjacent waterways, leading to algae blooms that can get into the air, creating when it gets through evapotranspiration and leading to ammonia in the atmosphere. So the adoption of USG should generate both environmental and productivity benefits. In the intervention, sort of a standard technology adoption promotion effort of farmers in treatment villages receiving information about the new technology, some price discounts, and then making sure that the technology is available within those villages. So on the right is just it shows that the treatment led to 28% of farmers in treatment villages adopting USG in the first season. So we were motivated after this initial RCT of going beyond the survey data. So in sort of typical form, the survey data was pre-post collected roughly a year apart. We actually didn't find productivity benefits materializing after that first season, largely because the farmers didn't really adopt all the other sort of necessary complementary inputs that are required to make USG sort of as productive as it is in test plots and on perfectly implemented agronomist plots. Also, the survey data did not measure land use or deforestation well or really at all, and also control and treatment villages were not the universe of villages in the study area. Okay, so when we wanted to look at forest cover, we wanted to understand the long-term dynamics of productivity benefits. That's sort of a crucial factor if we think that the intervention is going to lead to any sort of difference in land use or forest cover change. And we wanted to study deforestation in the study region, and also we were interested in what happened in households and villages that were not necessarily included in the original study, but were still in the study area. So enter Earth observation data, which would sort of help us with this. And the core challenges, I think, was like alluded to a few times yesterday, is how do we link the RCT data with Earth observation data? So the RCT is a village level randomization. And there's an information treatment we might be interested in or might be concerned particularly about spillover effects of that information and diffusion of that technology across time and space. The deforestation data is at the pixel level. So the common approach in the literature is to draw circles around villages, sort of define a buffer, and then you aggregate the land use data up at the village level. The question is, how big do you draw the circles? It can lead to measurement error, coding areas of land as treated when in fact, perhaps they weren't treated, or vice versa. And then also, how do you deal with overlapping circles, which is particularly acute in our study area, as you can see in this picture. So the radii of these circles are the 75th percentile of the distance between households and the rice plot. So the survey data did not include GPS coordinates for each of the rice plots, but we did have information on how long does it take you to travel between your house and your rice plot, and that varies at the village level based on the characteristics of the village. And you can see that there's quite a bit of overlap here. So if we were to pursue this common approach, we'd have to figure out a way to partition a lot of these circles. And there's some circles that are completely subsumed by other circles. And particularly in the middle, there's areas that seem to be very intensely treated by being proximate to multiple treatment villages. So in addition to those challenges, when you aggregate everything up to the village level in a kind of a smaller scale RCT, you might run into statistical power problems, which I think at least my reading of the literature on this, that's a common problem or a common sort of challenge with a lot of studies in this area is finding relatively meaningful treatment effects, but that aren't really distinguishable from zero. So we decided to do is sort of, instead of do everything at the village level, let's perform our analysis at the pixel level, and then come up with a way to define treatment exposure at the pixel level. So we do this with the following 4 steps. We use this information on travel times and distance between homes and rice plots. So this is a key sort of data requirement for this approach, but something like this information or something akin to this survey question is commonly found in a lot of household questionnaires. I think we would typically include that in a survey. And then we fit a distribution on these distance measures. We in particular use the gamma distribution. We find that fits the data relatively well. And we define a probabilistic measure of each pixel's exposure to treatment in a given village. We base this on the fitted gamma CDF. And then we sum over all of those surfaces to generate a continuous measure of treatment exposure. So on the right here is just a plot of that. So we're drawing big circles, 15-kilometer circles around the village, the study villages. This defines our study area for this study. And you can see purple areas are places that are not treated, and yellow areas are places that are treated up to 3 times, or approximate pixels that are approximate to at least 3. Or at most 3 study treatment villages. Okay, so the estimation approach, we're using the deforestation data at the pixel level. These data are observationally irreversible, so they don't characterize regrowth. So we use a hazard regression that basically is the probability of forest loss at the pixel level, and then a kind of basic difference in difference specification built on that. We measure productivity with NDVI. We use a variety of different vegetative indices, the median and max values over either the calendar year or the growing season. We also use EVI, MSAVI. could discuss a lot about those. Unfortunately, sort of all those results kind of point to the same results as I'll show. And critically, we analyze heterogeneity based on at the pixel level based on baseline tree canopy cover in the year 2000. So trying to understand how do these results differ based on the canopy cover prior to the intervention. And I think this is like really critical. Doing this analysis at the pixel level really enables this level of finely detailed heterogeneity at a fine, very fine landscape level of detail that would not really be as easily feasible if you were to sort of aggregate all that data up to the village level. And critically, this sort of shows, as I'll show you, doing this analysis in this way allows us to, really uncover this intensification response for this. So here are deforestation results. In column 1, no effect on average, but when we sort of start to look for heterogeneity based on pre-existing landscape cover, we see that in densely forested areas, exposure reduces tree canopy loss. The magnitude of these effects are such that in densely forested areas, exposure reduces tree canopy loss to nearly zero, almost eliminates it. The full interaction with the distribution of tree canopy loss confirms these results too. And column 4 is when we use the full sample of all of our pixels. A cost of doing this analysis at the pixel level is that you have a ton of observations, and so especially when estimating this hazard regression involves quite a bit of computing power to do this. So for most of our analysis, we take a 10% sample of pixels. This sort of just visualizes this heterogeneity, which we think is consistent with intensification. So in areas with baseline tree canopy density that's relatively low, we see actually an increase in the loss rate, so an increase in the loss rate of canopy cover, but in more densely forested areas, that loss rate is negative, a reduction in that loss rate. And so these are the productivity results. A lot of words on this slide. We find generally that the treatment exposure increases measures of NDVI, and this is concentrated in pixels with less baseline canopy cover. So kind of the mirror of the deforestation results. The same results whether we use the median or max over the calendar year or just the growing season, July through December. We use different measures, EVI, which it corrects for different background atmospheric effects, background noise. These effects we would expect them to be sort of the opposite signs of the NDVI results. This is precisely what we find. On sparsely covered land, EVI falls. On densely covered land, EVI falls. Then we use these two sort of composite measures, or the ratio of the max EVI and NDVI over the growing season. So we would expect an increase in agricultural productivity relative to tree cover. This should reflect lower values of this measure, and this is exactly what we find: evidence of increased productivity in pixels with less dense baseline canopy cover. And then we use the difference between the max NDVI and this modified soil adjusted vegetation index, MSAVI, which addresses soil noise. Many people have mentioned this limitation of NDVI yesterday. And again, we find evidence of increased productivity in pixels with less dense baseline canopy cover. And so these are just some pictures that sort of visualize what we think is going on here. Does this thing work? Okay, great. So on the left, this is a picture of a zoomed in area of the study region in 2015, and on the right in 2021. You can see sort of areas up here which are densely forested cover, similarly dense after the intervention. Areas around here, areas adjacent to farmland, maybe less dense forest cover, similar here, which are now sort of cleaned up after the intervention. And the idea that we have in mind here is that you're a farmer who has relatively low productivity. There's some trees around your plot, maybe trees in your plot. It's not really worth the effort and cost to clean that out. New technology comes along, productivity improves. well, maybe it's worth sort of cleaning up that and getting more out of my plot, but it's not worth sort of cutting down all these trees over here. So this is the sort of heterogeneity that we're able to identify precisely because we're doing this analysis at the pixel level. And so just to conclude, really with an invitation. So we want to extend this analysis to more context. The results that we showed are heterogeneity is really important. We find that the results depend on pre-existing canopy density, but you can imagine a lot of different factors of heterogeneity here: input and output market access, agroecological suitability for the crop, property rights, and also we have in mind not just agricultural interventions. So you can imagine improved cook stoves or an intervention that sort of promotes that that could also change and influence land use patterns. So if you have access to existing RCT data that seem to fit this mold and have the data requirements, let's talk. I think what's exciting about this is that there's no need to collect more data. That's what's like, I think, a general theme of these few days is there's a lot more that we can do with existing data that has already been collected, cost a lot of money to collect. Let's see what more we can learn about it. So, if you're a funder who's looking to learn more about these things, to address these triple challenges, I think there's lots to learn about. So, thank you.
Thank you. So about 5 minutes for questions. I'll let you manage.
Yeah. All of a sudden there was like 5 before you. Okay. Go ahead. Oh, sure. Yeah. Let's do that.
Thank you very much. That was a very good, very interesting paper. It's quite similar to what I've been doing with Professor Ariel. I face some challenges that I would like to understand how you were able to overcome them. For instance, to settle the buffer between the treatment and the control, do you account for both the plot and the house location of the farmer, or just the plot? And after you set the buffer between treatment and control, when you run your balance test, do you obtain no imbalance at all? I would like to understand, because it's very hard to, once you settle the buffer, then that affects greatly your balance results. Thank you.
Great. I'll take a couple. Yeah. There was. Yeah, go ahead.
Yeah. So I just want to understand a little bit. So the randomization was done at the village level, and then it was offered to the farmers, the technology, but was there some self-selection that could have happened with the farmers that actually ended up taking up no? And then the other thing is, in terms of how persistent was the adoption, do you have anything in terms of how long after the program the farmers still continue using the enhanced urea? Because I'm not convinced about the story of how this would lead to less. It seems like unless there was some persistent adoption, some additional income that was coming in the farmer, for them to start thinking about extending to areas that were a little bit more remote. I'm not quite sure if this is what's driving those results. So if you can maybe talk about that a little bit.
Yeah.
Okay. Yeah. So the question there, and then maybe I guess this. You had a question, or you just want to have other people having questions?
Very quickly. Of course, rice may drive deforestation, and what we've seen in this image is mainly villages along the river, and so forests are not just forests, are riparian forests. They are in fact, of course, on
carbon, but also on the quality of the water. Would you consider to separate this riparian forest to other type of forests that you would see because of the impact is, I mean, water was not said at all in this presentation. I think it's also a big challenge for this type of impact.
Sure.
About the work on the CIMA, but taking into account the non-repetitive of deforestation, and it's quite new as far as I know. Has it a strong influence on the results? You test both things? Because
many works used a different approach, and do you think that it significantly changes the results that we observe, that we have for deforestation studies?
Sorry, so the nature of the data and
because it's non-repeatable,
yeah.
you used a different model than previous ones, following Garcia and Helma.
Yeah.
And how does that changes your results? Thank you.
Sure. Okay. So for our main analysis, we don't actually use buffers around the areas those are just sort of for illustrative purposes. But the data that we know where the household is, but we don't have GPS coordinates of the plots. We have that survey data that says, well, how far do you have to travel to get to your rice plot or plots, and then we use that. We can show we can aggregate up, and we show balance of the canopy cover data pre-intervention. This approach also, in addition to the randomization at the village level, there's identification also relies on balance in the distance measure as well, and we sort of show that as well in the paper. And so I think that captures that. The persistence of adoption, that's like a really important thing. We actually tried to sort of like fundraise to go back and ask these farmers, like, what are they still doing? Weren't able to sort of do that. But one, I think, interesting thing is the company that we worked with in the initial RCT, which was conducted more than a decade ago, they don't sell prilled urea anymore. They only sell USG. And it's used for not just rice, but maize as well. That's one anecdote to sort of suggest that like the company that was selling it, they've like completely, not marketing the old technology anymore. They're just marketing the new technology, which is, it is what it is, but that sort of indicated that, yeah, farmers are still using it. They haven't just like shifted off of it. I didn't quite catch the question on water use and what you were saying. So maybe we can talk afterwards, or if you can quickly clarify or something. Okay. And yeah, we didn't run the analysis of like, we sort of knew what the data, what they were, and sort of estimated it with a hazard regression. We didn't try it with just sort of this more vanilla approach. So I don't know how they would change if we were to incorrectly treat the data as if it was just a binary variable of some sort. But basically at the pixel level, once deforestation happens, it's gone from the data set. So yeah.
Great. And now, before turning to Joel, I am going to say one word about the paper that we're missing, which is also deforestation in Ethiopia in this case, and in large scale. So this team of authors, mostly Ethiopia based, in fact, got their hands on kind of detailed land acquisition. So kind of the shape files of the large scale land kind of I guess not donations, but land right assignments by the state with administrative delays that they can then kind of exploit. And so their result, in fact, is so. I'm saying this so I encourage you to look at the paper since we don't get the presentation. Tell a different story, which is one where the deforestation happens after the land rights, but the agricultural productivity does not go up because then there is further delays in actually putting that land to good use. So it's an interesting kind of contrast to what we just heard. And so with that, back to West Africa and to Joel.
Thank you. There we go. So this is joint work with Abdu, who is wrapping up a postdoc at Princeton, moving over to the World Bank. Marco at Berkeley, Samba and Mamour at Université Gaston Berger in Senegal. Alon, and then I wanted to especially mention Elizabeth Betty Sadule, who sadly passed away soon after we finished this project. She's such an important figure in development and, an amazing mentor to Abdu and me and many others. So I wanted to especially mention her. But yes, back to West Africa, we're looking at irrigation infrastructure in Senegal. Oh, maybe I need to, where's there? Can't click through the slides. There we go. So kind of motivating this similarly to Jeff, I guess that's maybe not super surprising, but I guess what we're focusing on here is that there's kind of some momentum around this idea that irrigation could be both sustainable and like a real boon to agricultural productivity in Africa. But there are questions, as we saw yesterday, about kind of the long-term feasibility of these projects or sustainability in the sense of like, can they continue to deliver the benefits that we think they could deliver? I guess to preview a little bit, we're going to find really heterogeneous results in terms of some projects are very successful, some aren't. And so what are the constraints that are driving that heterogeneity? So we're looking specifically at irrigation infrastructure development along the Senegal River on the Senegal side or within Senegal over the period 1988 to 2019. So one very nice institutional feature of this setting is that development along the Senegal River is managed by a government agency, SAID, who even for the private projects along the river keeps track of development. So we have nice administrative data on when and where these irrigation projects are, well, where they are and when they were completed. And we combine that with remote sensed data to generate high frequency land use estimates. We're going to do some event study analysis to look at what happens to land use on irrigation projects after they're completed. And then we're going to getting into this question about why are some successful, why some aren't. We're going to classify projects based on their patterns of land use. And then particularly among the kind of less successful projects, we did a survey with farmers asking them about what was going on that was limiting their ability to use the land productively. So quick preview, we find big but not huge effects on cultivation rates. So going from somewhere from 4 to 10 percentage points, depending on the season, to about a 25 percentage point increase. So going somewhere to like 30 or 40 percentage points in terms of how often this land is cultivated. We have a little bit of evidence that irrigation reduces sensitivity to weather shocks, which is not super surprising, but useful information. Very positive, I guess, from a climate adaptation standpoint. And then the kind of second half is documenting this heterogeneity that is super wide in terms of some projects just like never produce anything, and some projects are incredibly successful, and then there are a lot in between that have really intermittent utilization, which was an interesting pattern that we found. So then we go and survey farmers, particularly on those places that that are either basically never used or exhibit this really intermittent pattern of use, and find that water access is really important for, particularly for the never used land. So kind of echoing what we heard yesterday. But then that financial constraints are a really important driver of the intermittent land use. So turning to the data, like I said, this is a really nice setting for this question because of this kind of centralized agency that has access to information on when and where irrigation development took place. So we have these shape files, vector data sets of where these irrigation projects are and when they were developed. You can see that there was this big wave in the late 80s. And then we had kind of different waves at different times, maybe around the turn of the millennium. We have some in the late 2010s. So there's really consistent development throughout the entire sample period, and over a pretty large area too. So in, I guess I should mention something about what's being grown here. So mostly it's going to be rice, but there is some horticulture as well. So that would be stuff like tomatoes. There's like potatoes, there's onions, definitely a lot of onion. But I think the main crop that you should have in mind is rice. And then you can kind of, I guess it's hard to see here, but there is this interesting mix of really large agribusinesses with kind of smaller, smallholder type agriculture as well. I guess the reason why you can have irrigation here on such like a large scale is because of two dams along the Senegal River. One that prevented the flooding that would happen most years, and then another at the mouth of the river that prevents salt water from coming back up, and helps basically make sure that that water is usable for irrigation. And then a picture of the one of the canals along the river. So we're going very, very simple in terms of the satellite imagery. We used Landsat because we're going back to the 80s to do this. We used every available Landsat or tier 1 Landsat image that was available for the study region. And like I said, very simple. One thing that I learned from doing this project is that when you're going that far back in time, simple is better, because in some years we only have 4 images, something like that. And so the measure that we're going to use is just a threshold in NDVI. So we're just going to say land is cultivated if the NDVI reaches above 0.3. That's another kind of special thing about this setting, is that because the background vegetation is so low, we can just look for, does the NDVI ever get above 0.3? And it's a pretty reliable measure of if the land is cultivated. We looked in places outside of irrigation projects, and almost never does the NDVI get that high. So that's why one reason we're able to go back in time so effectively, even though we have very few images, is because if you're growing something, it doesn't take that much to get above 0.3. And so even if you don't get, if you wanted to say something about yields, then the phenology is really important. You might want a much more dense time series. But to just get above 0.3, you can basically observe it any time during the growing period. And so that's kind of why this works. And also we know where we're supposed to be looking thanks to the administrative data. And then, sorry, I forgot to say, but we're just going to average, across pixels within a project, or specifically, there are sub projects that are called development units, and that's going to be the unit of analysis here. So just some visual examples of how this works. In 1984, you can see none of these projects existed yet. There's basically no vegetation. And then jumping forward to 2020, a lot more growing, some that are not really super successful, like that one that's highlighted in pink, and then some that are just like totally green, like the one that's highlighted in yellow. This is just going to be another visual example showing how we go from NDVI to like our classification measure and what that looks like intuitively. So this is just going to be RGB, so you can kind of see intuitively where is stuff growing and where it isn't. Here's NDVI, so looks like it highlights the stuff that looks like plants. And then here's our threshold classification. So pretty intuitive. So our main kind of causal design is going to be this difference in differences, but here's just the it's always nice when you can just look at the raw data and see the result. So here's just comparing projects that we're looking pre-project completion compared to post-project completion, looking at the NDVI profile throughout the year. This is, focusing on later years where we have enough, like a denser time series of imagery, and we can kind of reliably get good estimates of the NDVI in each month. And you can just see this big increase in NDVI throughout the year, but especially, you see it. I guess maybe the main thing I want to say is that you see it throughout the year. Every point in the year, you have a higher NDVI, and that's because there's more being grown in every season. And so here's the different the event study estimates. We used Borussia, Jaravel, and Spies, but it doesn't. I would be surprised if it really mattered which one you used here. It's kind of a canonical, I guess, event study. You see these nice flat pre-trends, which is not surprising because it's really hard to grow anything, except maybe during the rainy season. There's a little bit. It's really hard to grow anything if you don't have irrigation. But then you see this pretty immediate and large increase in cultivation rates that continues to grow out to 25 years post project completion. Again, including during the rainy season. So this irrigation augments the little rain that you do get during the rainy season. Just a really quick result on weather shocks. So like I said, they're mainly growing rice, and there's some existing evidence that rice has this asymmetric temperature response where it doesn't like it doesn't like hotter minimum temperatures. So it doesn't like hot nights, but it does like hot days. And so so you see that kind of more dramatically prior to irrigation compared to post-irrigation. There is no real response in terms of temperatures. Then, so big increase in cultivation rates, but going up by 25 percentage points, 30 percentage points, something like that. Definitely not getting to 100. So what's going on there? Well, here's like a picture of an unused plot where you can see like some salt on the surface. If you aren't able to drain the land properly, you end up basically just getting all the salt soaked up to the top of the plot, and then it dries out, and then the salt is just left on top, and it's really hard to deal with that. This is an example of one of the things that can go wrong depending on how the infrastructure is managed. We have, like I said, a really wide variety in terms of the experiences of these projects. So looking on the left, we see a very successful project. You know, they had 1 year where they kind of fell off, it seems, but other than that, super high NDVI throughout the entire time series after the project is completed. We have one that's a little more, we call it medium use. You know, it looks good, but not quite as good as the high use one. And then we have these other less successful projects, a low use project, one that basically never takes off except for maybe the last couple of years. And then we have these intermittent use projects, which are perhaps the most interesting, where it just bounces around year to year. And they're actually the most prevalent type of project that we see in the data. Even I think this is looking over the entire time series, but even if you only look at post 2010, you see a pretty similar pattern. So these low and intermittent use projects make up quite a bit of the sample. So we went out and asked farmers what's going on. The way we did this was we went to a kind of contact person in these development units, went out with the government agency and asked them for phone numbers of farmers. So we knew from the satellite imagery which places to go to. We went to those places, asked the contact person for phone numbers of farmers who don't use their land so much, and then interviewed them over the phone. I guess here we're just saying there's lots of different constraints to to cultivation, but the main one in terms of land that's never used, that's that first column, is something related to water. So the waterway isn't well constructed. There isn't enough water at the source to be able to actually use the canals. And then you can see financial constraints are relatively more important for the intermittent use, the ones that bounce around. And so we asked not only about constraints, but also about what it would take to fix this. And specifically, like, could you fix it? Could your producer organization fix it? Or does somebody else need to fix it? And so for these irrigation, water access problems, it's beyond the producer organization. Somebody else needs to come in and fix this. And then for the temporarily unused, that intermittent land use, where financial constraints are relatively more important, the farmers say and believe that their producer organization plays a more important role. That makes sense because one of the original kind of like impetuses for forming these producer organizations was to access government-provided agricultural credit. So it aligns well with that kind of logic. So yeah, that's basically it. I guess the main things that we found were that the irrigation does really increase the cultivation rates of land, but there's huge heterogeneity, and there's a number of constraints related to both engineering as well as like financial access that constrain land use on some project, or I guess the majority of projects actually. Yeah.
Thanks. So we have about 4 minutes. I'll let you manage.
In terms of when the project was constructed and where they fall in terms of, so are these projects being like rehabilitated in time, and how would you handle that? And then also in terms of exactly, do you see that newer projects might be in better use, or is it more the older projects? And then also in terms of, did you look at all in terms of the water user associations? Were they collecting like the fees that they were supposed to collect? Anything about the governance that you can tell us a little bit about these, about maybe, to see if there's different governance arrangements for these different types and where they fall in terms of being used or not used?
Have so many plots that have been irrigated since 25 years. And if it's actually related just to those plots being implemented much earlier or something else. Yeah, on that. Thank you. I didn't use the mic.
Thanks for the nice presentation. Actually, I had a question related to selection bias. I mean, to the extent that the shapefile that you're observing are the shapefile that were produced by the administrative unit. And I was wondering, how sure are you that all the irrigation projects for which you have a shapefile aren't just those where, I mean, let me put it the other way around. How confident are you that all the irrigation projects that failed have a shapefile? Okay, so thanks.
Yeah, thank you for the interesting presentation. Just a question on the aggregation method you use for looking at NDVI. I just wondered if you found any differences in using the seasonal or annual aggregation, especially because there might be different timings of growth for different crops. I'm not sure if that's the case in this location, and then also the actual method of aggregating, whether you use you said you use the maximum. I wondered if there's any difference when you use median or any other statistics. Yeah, thank you.
Yep. So you have 2 minutes.
Okay. I'll go quick.
But we'll get the last question in the back.
Were you able to distinguish between, in terms of use, between rice and horticultural crops?
I'll go quick. Stuff about project construction, rehabilitation. A lot of these were rehabilitated. There were kind of 2 waves of rehabilitation in the early-ish 2000s and then in the early 2010s. We tried to get data on when exactly, or more so which projects were rehabilitated, but weren't really able to do that. It would be interesting to look at that. But I think that does tie in with the